Okay, good morning, everyone. I think this is where we left off last week. I wanted to show you the motion of Mars as an example. Jupiter and Saturn will have exactly the same pattern, except just the sizes of the difference in epicycles will be different, but the basic idea is the same. So here is Ptolemy's motion of Mars. And the first thing that we notice is that the epicycle is much bigger than the difference. Yeah, there's no reason why that can't be. This is a system of tremendous flexibility. And you see how close Mars comes to the Earth and how far away it gets to the Earth. And so by using that very large epicycle, we get the very great change in brightness of Mars. And that's the reason why the epicycle is so big, is to get that great change in brightness that we saw. So here's the path, much simpler than the path of Venus. And you won't be surprised that there is where the retrograde will become, right there in that loop. And notice that that loop is when the Mars is closest to us. And so therefore we will get the retrograde. We get the brightest at retrograde. So let us take a look. Watch the blue line, which is our line of sight against the background stars. And we're going around quite nicely, quite evenly. And when we get into the loop, we will go backwards. There's the retrograde motion. Okay, very elegant, very nice. And we're getting it just when we need it. We're getting the retrograde when we are at the closest, when we are at the brightness. The other thing that we need, right, remember, is we have to be in opposition with the sun for Mars, Jupiter, and Saturn. That was the third condition. So let me go ahead and show you that. What we're going to do now is put the sun in the picture. Here's the Earth. Here's the deferent of Mars. Here's Mars itself, and now here is the sun here in brown. Exactly the same picture I've shown before, but we now have the sun moving the way it should, according to the sky watchers, according to all of the records. And so here, there is the retrograde loop. There's the sun going around. And right here, as we get into our retrograde, where we have to be at the brightest, where Mars is the closest, yes, we are in opposition. Okay, we are in opposition. So we get the three conditions correct. Retrograde at its brightest at opposition of the sun. That is, Mars is on one side of the sky and the sun is on the other. So a very nice, elegant solution. There's one more piece of pretty geometry that I'll just show you very briefly. How does Ptolemy get this connection with the sun using this parallelogram? What Ptolemy states is that whatever direction the Earth has to the sun, whatever that direction is in the sky at any time, he wants the center of the deferent to have the same direction to the planet Mars on the epicycle. And this is how he controls the motion of the epicycle with that geometric fact. However, we see the sun in the sky in that direction through the fixed stars, then he wants to use exactly that same parallel. These two lines will be parallel, so that it'll determine where Mars is on the epicycle. And given that, we get the combination that we need right here, that we are in retrograde at brightest in opposition to the sun. Okay, very pretty. And just one more comment. You may say, boy, Peter, you're very smart. How do you know how to program all this Ptolemy stuff? Well, I'm not as smart as I look, guys. What I've done here is I've taken the right solution. I've taken Copernicus' solution and simply programmed it with the Earth in the middle. Okay, I have not actually built Ptolemy's system. Okay? I'm not that smart. But I do know Copernicus' system. I do know how far away the Earth should be from the sun. I know how far away the sun should be from Mars. And therefore, these measurements are all correct. If this is 1 AU, then this is going to be 1.5 AU, just the measurements that we're going to see in a minute. So I'm really programming this using the modern solution, simply just putting the Earth in the center. That's all I'm doing. I'm cheating here to get these models correct. Okay, any questions before we leave Ptolemy's system here in detail?
Peter, was there any effort spent in the early years in Ptolemy's time and afterwards to explain why the planets would follow these motions? I mean, since then, we've got the notion of gravity and the attraction of the different bodies.
Yes, this is a good question, Mike. This is one of the central questions I want to raise, actually, in our class. The only thing that we have going here is the edict, the dictum from Plato, that first of all, that all motions in the heavens, since they are perfect ether, must travel in circles or combinations of circles in constant speeds. We're told that we must have that. That is the structure of the universe. And he said, go ahead, you mathematicians, astronomers, and build a model to save the appearances. Plato made it very, very clear that we'll never really know what's going on up in the sky, in the heavens. It's too far away. It's inherently unknowable. But we do have all these records going back. We do see the sky every night. And we can certainly build a model which will save the appearances, which will describe what we see in the sky. And that's what this is. This is the most successful solution to that. And in fact, ultimately, the only solution. All the other ones died away because of this great success. So that's what we're working on. We're working on the mathematicians obeying Plato's cosmology of circles, combinations of circles at constant speeds, and to save the appearances is what they were told to do. They were not told to go ahead and figure out what's really going on, just to save the appearances. And this made everybody happy, because that's what the astrologers wanted. The astrologers wanted to know where things were at any time in the future and the past, so they could do, their horoscope kind of thing. And that really did satisfy the intellectual needs of the time. So there really was not even an attempt to really understand what was going on, because that was felt to be inherently unknowable.
Am I being unfair to think of this as a universe based on geometry rather than physics?
For sure. I think that puts it very, very nicely. I think that puts it very nicely. And we could say the same thing about general relativity. Yes, it is very interesting how we've come full circle. All right, so let us go to our discussion of Copernicus, the founder of modern astronomy. And I will try to back up this claim that he is, in fact, the founder of modern astronomy. Here we have, again, one of the most famous pictures in the history of science. This is a diagram from On the Revolutions of the Heavenly Orbs of 1543. This is his great masterwork. And you can see here is the Earth going around the sun, with the moon going around the Earth and all the other various planets. Okay. This is a simplified picture. This is not the final picture that you would get by going through all of his math. This is a simplified picture that he's showing, the layman just perusing the book casually, just to get the basic idea. Okay, so here is Nicholas Copernicus's dates. Born and raised in Poland. He was born and raised in this area of Poland here in the north. He was educated at Krakow, one of the great universities of Europe at the time, particularly in the science and astronomy. He had one of the best educations money could buy. He was also educated down in Italy, went to the great universities down there to study medicine and law. And finally, he wound up here. He wound up in Framburg, right here on the coast, right here. You can see the Baltic Sea is right here. And this is where he spent most of his life after finishing his travels, and this is where he did his work. He was a canon in the cathedral up there in Fromberg. You can see a bit of his biography. Basically, he was raised by his uncle, who turned out to be a very powerful person in the region, really the lord of the region. He was the bishop of the whole district, and he took care of his nephew. Clearly, Nicholas was his favorite nephew, gave him the best education money could buy. He was no yokel. Copernicus is no, North yokel. He was a highly educated man and very well known in intellectual circles of Europe. And he was given a nice cushy job by his uncle to be a canon up there in the cathedral, not quite a priest, but someone associated with the administration of the cathedral and all of its grounds and all of its properties. He also studied medicine. He was the personal physician to his uncle for a while. He studied canon law and law in general, and worked as a minor diplomat for his uncle. Since his uncle was really basically the lord of the area, he did quite a number of small diplomatic missions in the area for his uncle. But finally, he did settle down just as the canon of Fromberg and was left to his own devices, and was able to pursue his real great interest that he had his whole life, which was astronomy. And yes, to live in interesting times, right? Take a look at the events that I just pulled out, clearly not at random, but events that happened between his birth and his death. This is quite an amazing list, right? As you read this, this is some of the great high points of the Renaissance, of the Age of Exploration, and of the Reformation. So he was born and raised and lived during very much tumultuous times. And just a reminder, we've seen this picture before. This was a picture of the universe at the time. This is a famous book published at the year of his death. Not the year of his birth, the year of his death. This was still very much the prevailing view of the Earth being in the center, and the various layers. Here's the layer of water. Here's the layer of fire. Everything below the moon is La Lune. So here is the orbit of the moon. Here is the moon going on its epicycle. And Mercury, Venus, Sun, Mars, Jupiter, Saturn, and the fixed stars. And there we have the very simplified picture. Again, this is clearly not Ptolemy's picture. This is, again, a simplified picture for laymen as to what the basic structure of the universe looked like at the time of Copernicus's death. So let us take a look at Aristotle's theory of motion, because this will become relevant to us as we compare the two theories. We're not going to look at this in great detail. We'll need to know a bit more about this as we get to the overturning of this theory with the work of Galileo. But I think it's important to just show the overall structure of it right now. And that is, again, Aristotle is the master of categories, right? So we have basic construction, categorical construction of the earth, of the elements, of physical bodies. So all elements have a natural place in the universe. All elements have a natural motion going through that universe. And everyone has a tendency to move to their natural place. Moving to the natural place requires no force, requires no outside agent. It is in their nature to move in their natural motion to their natural place. That is the inherent nature of the basic elements. And the basic elements are earth, air, fire, and water. Everything else is made up of complex combinations of those in a kind of a chemistry. So the elements of earth and water, well, they have a natural place. Their natural place is the center of the universe. Why? Well, because they're naturally heavy. They have a natural heaviness, and so they belong in the center of the universe. Their natural motion will be straight down towards the center of the universe. Air and fire, they have their natural place up in those concentric circles above the earth, above the atmosphere. In the atmosphere, you have the water area, and then finally you have that so-called ring of fire above that. And then above that, we have the orbit of the moon, or if you like, the deferent circle of the moon. And that motion, that natural motion, is straight up, as we can clearly see, right? When you see smoke rising and fire rising, of course, the natural motion of air and fire is straight up. The ether is perfect and unchanging, as we know, and its natural place is wherever it is right now. That's its natural place. It's always perfect. So it always is where it should be. And its natural motion is at constant speeds, moving in circles or combinations of circles. Okay? And the ether is fundamentally different from the terrestrial elements. They have a fundamentally different nature. They have a fundamentally different motion. They have a fundamentally different place. You can't be any more different than earth, air, fire, and water, which at least have some things in common. At least their motions are both in straight lines. And the ether, where their motion is in perfect eternal circles. So the universe above, the moon and above, is made of this perfect, unchanging matter, only moving in eternal circles. Nothing ever changes in the heavens. It can't. Otherwise, it wouldn't be perfect. Otherwise, it wouldn't be this eternal thing that has been from time immemorial. So there's nothing ever changing in the world, in the heavens, at the moon or above. Something that everybody knew. That was everyone's comments. Well, of course, we've been looking at the heavens forever, and it doesn't change. So of course, yes, I agree. What could be plainer than that? And finally, we have as opposed to natural motion, we have violent motion, the second category of motion. Violent motion is only applied to earth, air, fire, and water. Of course, there's no violent motion of the ether. And how do you produce violent motion? Violent motion must be produced by some kind of an outside agent. Has to initiate that motion. Otherwise, all you'd have is natural motion. So forces of contact would be hitting something with something else would create that thing, a violent motion in the thing that was hit. Living bodies, we all have fire and air in us, and we have the ability to move proactively, and we can create violent motions. Bodies already in motion can, like I say, impact, strike something else, and create a violent motion in something else. And finally, the rotating of the sphere of the moon is also a violent motion in the sense of it is disrupting agitating the ring of fire. And that will give us a lot of the changes that we see here in the terrestrial world. And that rotating of the sphere of the moon will create a rotation and a disturbance of the ring of fire, which will bleed all the way down into air and ultimately into the earth. And this is where we get weather, for example, and fire and rainstorms and lightning and things like this. It all comes from that motion of the moon, is creating those kinds of changes that we have. And notice how static Aristotle's universe is. If it wasn't for this explanation of the rotating sphere of the moon stirring up the ring of fire, which therefore is kind of stirring up everything else, notice that otherwise everything in the world, the earth, air, fire, and water, would all seek its natural place and have no reason to move. There will be a layer of earth, which is the heaviest, covered by a layer of water, and then, and then a layer of air and a layer of fire, and the ether above would be moving in eternal circles, and nothing would ever change. The universe would be completely frozen and static, because everything would have found its natural place, and there would be no tendency for any movement. Yeah, it's quite amazing. But we're saved from that death of naturalness by the motion of the deferent of the moon, stirring up the ring of fire. Yeah, he is brilliant with his explanations, and everything there can follow from that. The ring of fire, therefore, will create all the disturbances, and the fact that we have things, happening all the time. Things are dying and growing, and all the cycles of life. So there's another reason why there could be violent motion. One of Aristotle's precepts, which you don't want to get into too much detail now, this will come when we look at the work of Galileo, is that one could ask the question, well, when I shoot an arrow, once it leaves its bow, why does it keep moving? I understand that the string of the bow pushed the arrow out, but after that, it's just floating in the air. Why does it continue to move? When I throw something, after it leaves my hand, why does it continue to move? It's not, being touched by anything, but yet it still moves. It's clearly a violent motion. It's not the natural motion, otherwise the ball would just fall down. Here, I've thrown it up in the air. It's moving in this kind of an arc. That's clearly a violent motion, not a natural motion. What's keeping it moving in that motion for a while? And this was a great weakness in Aristotle's theory, because Aristotle said that every motion at any instant requires some kind of an outside agent. Well, in response to that criticism of Aristotle's theory, a new idea was put forth, the idea of impetus. That is, that the object was given an impetus to continue to move in that direction, and that would finally peter out as the impetus died away, and then natural motion would ensue. But this idea of impetus was what was the idea that was imparted to the body by the agent that created the violent motion, and that stayed with the body in some way as it, petered out, deteriorated, and after the impetus was all gone, then finally natural motion would pursue. And this is exactly how people saw, for example, an arrow being thrown. It would go out straight for a while, and then ultimately just fall down and just go down straight. Of course, it doesn't really happen that way, but it is amazing the difference between what people will take as explanations because they're following all the correct precepts, and kind of what you see in your own eyes. And you can live in this world which you can accept both in some kind of vague way and not give it any great criticism if that's not what you do. And these ideas, although they are wrong and don't even hold up to close scrutiny, if they're not given close scrutiny, they can simply survive for forever. Sound familiar with other things in the world? Yeah, I think so. And so, again, with this idea of impetus, that the violent motion will proceed as long as this agent is continuing to act. The simplest case is if I push a book along a table, as long as I keep pushing, the book will move. As soon as I stop pushing, the book stops. So, perfect example of that. I need that outside agent to continue to work to have the violent motion go on. Of course, you could ask the question, what happens if I push the book along the table and it moves for a while? It slides along the table after I stop pushing. What's keeping that moving? Aristotle had an answer with the air kind of getting behind it, pushing it for a while. Very hokey. Even he didn't like the idea, but it was the best he could come up with at the time. And so therefore, over time, we have this idea of impetus developing to try to, supplement those reasons of how things can continue to move. Never mind a book sliding along a table. Imagine rolling a ball along a table, right? It'll roll even longer, move even longer than the book. What's the difference between the ball and the book? Again, we don't want to get into too much of this right now. We'll be talking about this in great detail when we look at the modern ideas of dynamics with Galileo. All part of our integrated story here, all a necessary part of the story in order to bring our great paradigm shift of the scientific revolution. Violent motion for the ether? No. There's no such thing as violent motion. You cannot have apply violent motion to the ether. Okay. First of all, it's unnecessary. The ether already has a motion, and it will continue that emotion eternally. But notice that we need no outside agents for the motions of the heavens. Going back to Mike's question, there's no need to look for something like a force of something. The heavens are moving naturally because that's how they move. That's their natural motion. Before we leave this, we can see that with the Earth being in the center, and why is the Earth at the center of the universe? Well, isn't the Earth the heaviest part of Earth that you can ever find? The Earth itself. So doesn't that belong in its natural place? What's going to move the Earth away from its natural place? So yeah, clearly the Earth is at the center of the universe. Where else could it be? It's the Earth and the water. These are the heaviest things in the universe. Has a nice explanation for gravity. Why does everything fall? Well, things are heavy. They're made of more of earth and water than they are of fire and air, and therefore they are naturally heavy, and therefore they naturally seek their natural place, which is the center of the universe, which happens to be the center of the Earth. And so things fall down. Buoyancy. Why do things rise in the water and float? Well, remember, everything is made up of some combination of earth, air, fire, and water. And if there's more, air with the water than there is earth, then some of these objects, although they're heavier than air, they'll fall down in the air, they're lighter than the water. And so they'll rise up in the water because they're heavier than air, but lighter than water. And so we have an explanation of buoyancy. Yeah, you can spin these ideas, quite effectively. But notice one thing about all these ideas that we've discussed so far. There's nothing quantitative about it. There's no numbers involved in Aristotle's ideas. Everything is qualitative. And that was perfectly fine with him and perfectly fine with everybody else. The only place where you'll find numbers is with the mathematicians. And who are the mathematicians? Those are the astronomers. They are the same people. Okay, they are literally the same people. Astronomy is a branch of mathematics. Astronomers call themselves mathematicians. They're referred to as mathematicians. Those people take measurements. They've been taking measurements with the sky watchers ever since time began. But to take quantitative measurements, to study the world, not really necessary. That's artisans take measurements. People who build things, if you got to build a house or build, those people take. But abstract thinkers who are trying to find the fundamental principles of the universe, no, we're not going to make any progress by taking measurements. That's not where the underlying knowledge is going to be found. It's going to be found in reasoning through our general principles, looking at fundamental observations. And that is the state of play until we get to the scientific revolution. And it supported people very, very well for a long time. And we'll see why that transition was made into the world of measurements. Okay, just a brief note, we should not leave, going into the Middle Ages until we at least get a mention of the great Islamic civilization. Their high point, intellectually at least, was from 750 to 1250. They introduced, for example, the so-called Arabic numerals from India into, first of all, into their civilization, and then brought it into the West. They certainly mastered and translated all the scientific works of the ancient world. Okay, most importantly, again, Euclid, Apollonius, and Archimedes, and Ptolemy. They not only translated these works, they completely mastered and generalized, and then went ahead and generalized all of these works. This, of course, would be a whole course in itself to look at the science and math of the Islamic world. And they extended the mathematical astronomy of Ptolemy, looking for different kinds of ways of making that same explanation that, that's trying to save the appearances. But interestingly enough, they never broke out of the Ptolemaic paradigm, right? They never broke out from the basic idea of deference and epicycles and eccentric points and that kind of stuff. They did not change the mathematical framework what they were working with, and therefore never made any kind of a qualitative leap to a different kind of mindset, although they were masters of the ancient world mindset and extended it very, very much so. And just to remind you, yes, all of the classical texts that first entered into Europe in the late Middle Ages were Latin translations of Arabic works. It was the Arabic translations of the original Greek that was available, and so there were Latin translations of the Arabic is what first entered into medieval Europe. Only later, when the original Greek works began to finally come into the late Middle Ages, where was people able to translate from the Greek directly into Latin. But for a couple of hundred years, the translation process was from Arabic into Latin. Okay, so Copernicus, where does Copernicus come from? Copernicus is a humanist, okay? Copernicus is someone who is educated in the classical world. He knows everything about the classical world. He reveres the classical world. He reveres the classical authors and their works, and all great knowledge, except for the Bible, can be found in those works. They are the heritage, the intellectual heritage that we have at the time of Copernicus. A lot of it filtered through the Arabic translations, but ultimately you're going back to the classical world. And the classical world did have, very, very well known to Copernicus and all educated people at the time, that there was a notion of a moving Earth. We went through this in great detail in the fall term, talking about the history of Greek astronomy, but Pythagoreans had the Earth going around the central fire, turning on its axis. And of course, the most famous one is Aristarchus. Aristarchus really had the whole thing going. He had the Earth going around the sun with the fixed stars very, very far away, and the Earth turning on its axis to create the illusion of day and night every 24 hours. Aristarchus laid out the whole thing. He was a great mathematician, and he's most famous for finding the distances from the Earth to the sun and the moon quite accurately with the moon, not so much with the sun, not because his geometry was wrong, because his measurements were wrong, because he just did not have the technology to take the measurements that he required. He was a great mathematician, but for some reason, nothing quantitative comes down with this model. Apparently, he just put it forth as a set of ideas and never worked on it mathematically. So it comes to us as just speculation, in a sense. Speculation from a great astronomer, from a great mathematician who never went ahead and built a mathematical model using these ideas. No one does until Copernicus. But these ideas were very, very well known at the time. Aristarchus's work, certainly with his work on the sun and the moon, those distances were studied as beautiful models of the way mathematics should be done, mathematics applied to the real world. All these things were well known, but and we don't doubt, by the way, that Aristarchus put these ideas forward, because they have none other than the authority of Archimedes himself. Archimedes was a younger contemporary of Aristarchus. He probably knew Aristarchus. Aristarchus could have been one of his teachers in Alexandria for a short time. And it is in his writings where he describes Aristarchus's speculations about the universe as I've just described. So we have no doubt that it is true, because we get it from the most important authority, scientific authority of the classical world, Archimedes himself. So what are the premises that the De Revolutionibus on the revolutions of the heavenly orbs, what are they based upon? All motions of the heavenly bodies, including the Earth, is in the form of uniform circles or combinations of uniform circles, right out of Plato. The center of the Earth is not the center of the universe, but only of gravity and of the lunar sphere. the deferent of the lunar cycle. The center of motion of the moon remains near the center of the earth. There's no common center to all the heavenly motions. He's going to need eccentrics. Yeah, he's going to need Hipparchus's eccentrics, just like Ptolemy did. The center of motion of the planets, including the earth, is near the sun, but the sun is the center of the universe. But these orbits that he's going to describe are eccentric to the sun. He's going to need that just the way Ptolemy did. The distance from the sun to the earth is imperceptibly small compared to the distance of the sun to the fixed stars. This is a remarkable statement. This is a remarkable assumption that the fixed stars are very, very far away, completely opposite from Ptolemy's universe, where we have the nested sphere, that the fixed stars are right behind Saturn. After you get to the epicycle of Saturn, right next door, right beyond it, are the fixed stars. Copernicus says, no, the fixed stars are very, very, they're way, way beyond Saturn. If you look at the distance from the sun to the earth, that's nothing compared to the distance from the sun out to the fixed stars. We'll see why he needs this assumption. The rotation of the earth about its axis accounts for the apparent daily rotation of the heavens. He says in his writings, wouldn't it be a lot easier for the earth just to go around as opposed to the whole universe to go around once a day? And the apparent annual cycle of the motions of the sun is caused by the earth going around the sun annually in the year. None of these ideas, guys, are original with Copernicus. All these ideas come from classical Greek astronomers and philosophers. Nothing here is original. Not even this business about the earth's distance to the sun being imperceptibly small compared to the distance out to the stars. Aristarchus made that very clear, that if you're going to have a heliocentric system, you need this assumption. And we'll see why in a minute. It's important to point out that Copernicus made no new empirical astronomical discoveries. He knew nothing more about the sky than Ptolemy did. He had no discoveries about the heavens that is, oh, well, because we've learned this now new, now I'm going to put forth. No, this is not what he did at all. Okay. Matter of fact, most of the data that he used was Ptolemy's data. Most of the data that he used to build his model, he found in the Almagest. He used some measurements from the Islamic astronomers, and he used some measurements of his own. Very, very few. Most of the data comes from Ptolemy itself. He puts forth nothing fundamental that the sky watchers would not completely agree with, for thousands of years. He's building a new conceptual model of the heavens, not with any new phenomena that he's going to add to the mix. That'll happen later. That'll happen as our story continues. Okay, let me go through his preface that he writes to the Pope, and then I'll stop for some questions. This is a masterpiece. This is 3 pages. I've sent you this as one of the Word documents. I actually gave it to you in 2 versions in that document. The first one is my excerpts. I took the 3 pages and knocked it down to 2.5 with some highlights, and then after that is the full 3 pages. It's a masterpiece of diplomatic work. He's writing this to the Pope, most powerful person in the world, and he's trying to sell his idea. He's dedicated the whole work to the Pope, and he's trying to tell the Pope, this is not so crazy what case you might hear. He's trying to sell his idea to the Pope. He grants that the idea of the moving earth is absurd and contrary to common sense, and he expects great condemnation of his theory when it's put out. He points out to the Pope that it's held back publication of this thing for 30 years. He wrote this thing 30 years ago, and it's been sitting in his desk. And the only reason why he's publishing now is because a lot of friends, powerful friends, he may point out to the Pope, cardinals and bishops, have encouraged him to publish this work. And so he's finally gonna. Why did he write the book? Where did he come up with the theory? These are the reasons why he gives the Pope. He says none of the old theories, none of the Ptolemaic theories in motion agree with each other. Well, this is because the Ptolemaic theory, right, has such incredible flexibility. Remember, you've got the size of the deferent, then how fast the epicycle point is going to go around the deferent. You've got the size of the epicycle, how fast the planet is going to go around the epicycle. When you get to the Islamic astronomers, they put epicycles on top of epicycles. You've got all those things going on. You've got the eccentric point. How far away do you want the path of the orbit to be from the actual Earth itself? How eccentric is the Earth going to be? And then, of course, you have the infamous equine besides the eccentric point, with the truly varying speeds. You have so many levers and dials that you can turn in Ptolemy's system that no wonder they don't agree. You would put forth a set of levers, and you would get your current data, and you'd produce your measurements, how big this should be and how fast this should be. And then you let it go, and you find out after 50, 75 years, the sky is not cooperating. Your model is no longer mapping very accurately the sky. It's beginning to drift further and further away from what we truly see in the sky. Time to reset the levers. Time to maybe try something different. And so, yes, the system grew and grew. The Islamic astronomers put more and more stuff into it, and was just getting more and more complicated. Something wrong there. They don't use consistent first principles and hypotheses. The principles are kind of floating, all over the place. If the system was correct, there would be a consistent set of principles, something simple. Plato says, well, that's the way it's supposed to be. They use methods that were based upon only apparent revolutions and motions. It's a very interesting statement that he says, that the methods that they use are just trying to save the appearances. They're just based upon the motions that we see. They're not trying to get after the underlying principles. They use methods which contradict the first principles of uniform motion. That's a direct swipe against the equipoint. That is saying equipoint cannot be used. You cannot use methods which contradict the first principles of uniform motion, which is these points, the planets and the epicycle centers going to the deference must move at constant speeds. That is the only way the ether can move. And the equipoint has some of those points moving at truly varying speeds. Can't be right. And the systems lack harmony and symmetry. He even says directly in the preface that it's like what the astronomers are doing is like they would take body parts, a hand and a foot and a head of different people, all very nice in themselves. It's a nice hand as a hand, but when you put them together, you build more of a monster than a properly proportioned human being. Mary Shelley's Frankenstein, right? Or 300 years later, there it is. That reference is right there in Copernicus. He says that he reread all of the works of the philosophers that deal with the motion. I highlighted the word reread. I got a kick out of that. As a humanist, of course, he has read everything that you could possibly read available about the ancient texts, but he points out to the Pope that he reread them. Again, his system explains most of the motions of the heavens as a consequence of seeing it from a moving earth. And there you have it, right? Most of what we see in the heavens is an optical illusion because we are looking at it, the heavens, from a moving platform. And here is the famous quote. The motion of the heavens follows logically and harmoniously from this fundamental premise, the moving earth. And the parts of the system are so closely related that nothing be changed without causing confusion in the other parts and in the whole universe. His argument is one of harmony and beauty and unity. It's not of new data, not of new observations. It's because my system is beautiful and it hangs together in a logical and a harmonious way. That's why it must be true. He's a humanist. He's a Platonist. He's not an Aristotelian. He goes back to the Pythagoreans and Plato. He lets the mathematics and the harmony of his mathematics say, this must be right. Look how beautiful and simple it is. This is what the creator would build, not the monster that the Ptolemy system has developed into. You know the famous joke, not a joke, it's a famous story of Alphonse the Wise in the early Middle Ages when he was taught astronomy. He was interested in astronomy, and they gave him some basic lessons in the Ptolemaic system. And he said, if I was around at the time of creation, I would have suggested to God a few simplifications. And finally, he correctly does, in the preface, talking to the Pope, he correctly anticipates the strong condemnation that his theory is going to get. He says he's not concerned. I will even despise their judgments as foolish because mathematics is written for mathematicians. Read astronomers there. They are the same people. And he leaves the judgment of his work to your holiness in particular and to all other learned mathematicians. So before I take questions, let me just read the last 3 paragraphs. I think they're just brilliant, and they really do capture what he's trying to get over to the intellectual world in general before he starts talking to his fellow mathematicians. Therefore, taking this as a starting point, I began to consider the mobility of the earth. And although the idea seemed absurd, he says, other people have thought about this idea, so I should take a crack at it myself. And so after postulating movements, which further on in the book I ascribe to the earth, I have found by many and long observations that the movements of the other planets, as assumed for the circular motion of the earth, and are substituted for the revolutions of each star, not only do their phenomena follow logically thereof, but their relative positions and magnitudes, both of the stars and of their orbits, and of the heavens themselves, become so closely related that in none of the parts can anything be changed without causing confusion in the other parts and in the whole universe. The next paragraph, this is his blurb. This is the blurb he wants to go at the back of the book, or in the front of the book. This is his publisher's blurb. Therefore, in the course of this work, I have found this plan. I describe in the first book all the positions of the orbits together with the motions which I ascribe to the earth, in order that this book might contain, as it were, the general scheme of the universe. Therefore, in the remaining books, I set forth the motion of the other stars and all of their orbits, together with the motion of the earth, in order that one may see from this to what extent the movements and appearances of the other stars and their orbits can be saved if they are transferred to the movements of the earth. And finally, his last paragraph, his last pitch to the Pope. If perchance there shall be idle talkers who though they are ignorant of all mathematical sciences, nevertheless assume the right to pass judgment on these things, as if they should dare to criticize and attack this theory of mine because of some passage of scripture which they have falsely distorted for their own purpose, I care not at all. I will even despise their judgment as foolish. But what I may have accomplished herein, I leave to the judgment of your holiness in particular, and to that of all other learned mathematicians. And lest I seem to your holiness to promise more regarding the usefulness of this work than I can perform, I pass now to the work itself. So there is the diplomat talking to the most powerful man in the world. Okay, we'll stop there for some questions and comments.
Was that final circle past Saturn on that original diagram that you showed, was that just the other stars rather than a planet?
That is the fixed stars. That is the celestial sphere. Exactly so.
Okay, thank you.
Okay, so here is the outline of the book. The outline of the book, chapter for chapter, virtually follows the Almagest. Yeah, he's following the same fundamental table of contents. Okay, obviously he has a moving Earth and a fixed sun, but the structure of the book is the same. The theory of the Earth's motion is admittedly difficult to comprehend, for it runs counter to appearance and to all tradition. But if God wills, I shall make this book, make it clearer than the sun, at least for mathematicians. From the book itself. So we find So we find underlying this description an admirable symmetry in the universe and a clear bond of harmony in their motions and magnitude of the orbits, such as can be discovered in no other wise. And he goes on to show some, some consequences. Okay? For here we may observe why the progression and retrogression appear greater for Jupiter than for Saturn, but less for Mars. Right? We'll see why this is very, very true, why Mars has a much wider swing in the sky through the stars than Jupiter, which has even more than Saturn. Okay? But greater for Venus and less for Mercury. Moreover, why Saturn, Jupiter, and Mars are nearer the Earth at opposition to the sun, why they're brighter in opposition to the sun than when they lose or emerge from the sun's rays in conjunction. Particularly Mars, when he shines all night in opposition, appears to rival Jupiter in magnitude. Yeah, they're both right, 15 times brighter than Vega, as we saw, being only distinguished by its ruddy color. Otherwise, it is scarcely equal to a star of second magnitude and can be recognized only when its movements are carefully followed. Okay? All these phenomena proceed from the same cause, namely the Earth's motion. That these are not the phenomena of the fixed stars provides their immeasurable distance compared to which even the size of the Earth's orbit is negligible, and the parallax effect is unnoticeable. Okay, well, I'll explain that in a moment. The twinkling of the stars also shows of their vast distance between the furthest of the planets, Saturn, and the sphere of the fixed stars. The sentence comes out a little bit opposite. What he's saying is the planets twinkle and the stars don't. And I'm sorry, the opposite. Planets don't twinkle, but the stars do. And it's chiefly by this indication that they are distinguished from the planets. Further, there must necessarily be a great difference between moving and non-moving bodies, right? The planets are moving, but yet the fixed stars are not moving, not in his theory, right? The celestial sphere is fixed. It's the Earth that's spinning once a day that creates that motion. And clearly, there must necessarily be a great difference between moving and non-moving bodies, right out of Aristotle. Okay, so where is he coming from? He's coming from the fact, why should we accept his theory? I think it easier to believe this, my theory, than to confuse the issue by assuming a vast number of spheres, which those who keep the Earth at the center must do. We thus rather follow nature, who produces nothing in vain or superfluous, often preferring to endow one cause with many effects. And I think I will demonstrate that very, very well in a moment. From one cause, we will have many, many effects. So, by the way, Copernicus did use small epicycles to shape his eccentric orbits. Right? He used all the mechanisms of Ptolemy except for the equipoint. He did not change the mathematics at all. Matter of fact, he pulled back from a lot of the math that was developed further. He stayed with his fundamental principles of Plato, but he did use some epicycles. So at one point he crows, he says that, our Ptolemy's system needed 55 circles. Mine only needs 34. So here's an example taking Jupiter. In order to shape the orbit of Jupiter, remember that tremendous flexibility of the deferent and epicycle, you can create an orbit that is eccentric, even dare I say oval. Okay, just a review of what we want to show here about the motion of the planets. What do we have here? We have for brightness goes with retrograde for all the planets. Brightness is with retrograde. For Jupiter and, I'm sorry, for Mercury and Venus, we have bounded elongation. So brightness with retrograde and bounded elongation. For Mars, Jupiter, and Saturn, we have any angular separation, but we again have brightness with retrograde in opposition. Brightness Has to go with retrograde and opposition. All three have to happen at the same time. And Ptolemy was able to do that. We've demonstrated that. Copernicus is going to do the same thing. Here, by the way, is the bounded elongation. It's very, very simple, right? When the Earth is looking at Venus and Mercury, it's looking inside their orbit. So certainly they're always close to the sun, right? One cause, many effects. If the motion of the other planets are correlated with the orbiting of the Earth and are computed for the revolutions of each planet, not only do the phenomenon follow therefrom, but also the order and sizes of all the planets and spheres and the heavens itself is linked together, that in no portion of it can anything be shifted without disturbing the remaining parts and the universe as a whole. As opposed to Ptolemy's theory, which you can twiddle those dials forever, and they have been. They've been twiddling them for 1,300 years. There's no twiddling in my theory. It's either right or it's wrong. I'm going for broke here. My measurements are coming from my measurements of the sizes and the orbits of the planets are coming from the measurements in the sky. One set of measurements dictates what my geometry must be. I have no choice. Once I take a bunch of angular measurements, I am stuck with my geometry. It's either going to save the appearances for the sky or throw it away. This is what he is claiming. There are no dials and buttons that you can twiddle with to change in my model. Matter of fact, the only ad hoc theory that he has, the one that comes out of nowhere in terms of Teradyne, is this business about the fixed stars being so far away. Since there's no depth perception in the sky, there's no way to verify that, to refute that. It's just an ad hoc assumption that he needs because of the lack of parallax. But this statement here, I think, is very, very powerful, that not only do the phenomenon follow therefrom, but also the orders and the sizes of all the planets and spheres. Remember, the spheres being the size of the different circles. And the heavens themselves are linked together, that no portion of it, anything can be shifted without disturbing the remaining parts in the universe as a whole. He makes a very, very powerful claim for his theory. And we'll get started with the pretty pictures, okay? Here, of course, you've seen, hopefully you've had a chance to look at some of the videos that I've suggested, and they go through this very nicely, the explanation of retrograde motion. It is purely an illusion. Retrograde motion is not real. It's an illusion because we're looking at the planets from a moving platform, okay? There's nothing, none of the planets ever go backwards for real. It is an optical illusion. And here's the, just a nice picture of Mars chatting the lines of sight, where you'll see the lines of sight go backwards as the Earth swings around and passes Mars by, because the Earth is moving around faster. Okay. One cause and many effects. Look how elegant, guys. Look how wonderfully elegant Copernicus's theory is. Here we have the sun, and here we have Venus, and here we have the green Earth. And here the red line is the line of sight. And look what happens as Venus swings around the Earth. As it approaches the Earth, getting brighter and brighter and brighter and brighter, and that swings around, there's the retrograde. The retrograde happens when it's at its brightest. Brighter and brighter and brighter, and at its brightest, at its closest, we get the retrograde. And look at the bounded elongation. Of course there's a bounded elongation. How far can Venus get away from the sun? It's inside our orbit. We're always looking towards the sun when we look at Venus and Mercury. Of course it has a bounded elongation. Bounded elongation, brightest at retrograde. Done. And Mars. Look how simple and elegant. The green Earth, Mars, and the sun. When will we have retrograde? Gets brighter and brighter, and right there is the retrograde motion. And retrograde and brightest at opposition? At opposition, yes, at opposition. Mars is on one side of the sky and the sun is on the other. We have retrograde motion when Mars is the brightest at opposition. Done. Look how elegant. Look how beautiful. Look how simple compared to Ptolemy's model. And finally, to shape the orbits, you need the epicycles. I warned you how powerful the epicycle mechanism is. Very easy to create an ellipse using epicycles. Nothing to it. Of course, I'm exaggerating this ellipse to see it very, very easily, but you get the idea of how you can shape an orbit in all kinds of ways by using Apollonius's device. And Copernicus used this device just as Ptolemy did, and all the successive astronomers, to shape and ovalize in a way to save the appearances, to get what truly looked like in the sky. Okay, any questions before we go on? One cause, many effects. I hope you're impressed. I know that you've known this ever since middle school, at least, or elementary school, but maybe you've never quite seen just how simple this system really is. And again, Copernicus, these are three-dimensional orbits here, right? These circles that is going around, these are full orbits. The title of his book is on the revolutions of the heavenly orbs. The orbs he's talking about are not the planets. He's talking about the three-dimensional orbs that are carrying the planet around. Okay, Copernicus is not breaking away from the fundamental cosmology of Plato, of the idea of the perfect ether. However, somehow or other, the Earth is sent out there like everybody else. How do you square this in your mind, that the Earth with air, fire, and water is out there with all the rest of the ether? Well, ultimately, you don't. Okay, but as a mathematician, Copernicus, if nothing else, just dodges these questions, just doesn't even try to address them. He's a mathematician, he's an astronomer, and he just wants to see a model, show you a model which will save the appearances. That's what his goal is. And he's not trying to solve all the questions that it raises. Questions, comments?
Peter, is there an assumption in either the Ptolemaic model or the original Copernican model that the different planets are all the same size and appear different simply because of the distance away? Or are they agnostic on that?
It's funny, the idea, even through the scientific revolution, Galileo does this all the time. Brightness is associated with size. So they have a notion that Venus is very, very big. Jupiter is very big. If it's very bright, it must be very, very big as well. They have this easy, simple, fundamental notion. And we'll see as we later, I don't want to get too far ahead in the story, but when the telescope was finally discovered and they actually see some of the sizes, when they see, for example, the transit of Mercury, that Mercury is this small dot that goes across the face of the sun, they are shocked at how small Mercury is. They had no idea it would be so small compared to the sun. So without any depth perception, without the telescope, it is virtually impossible to talk about the sizes of anything except for the sun and the moon, because the sun and the moon does have an actual angular size in the sky. So they, for better or for worse, they use brightness as a proxy for size.
That seems odd, because even before telescopes, you would think that you would have the common realization that a candle appeared brighter if you were within 5 feet of it than if you were 30 feet away.
Yeah, but you see, Copernicus is going to show that Jupiter is 5 times further away from the sun than we are. Jupiter is very, very far away, but yet it is the second brightest star in the sky. Okay. Mars is closer to us than Jupiter, but Mars only has the same brightness, in opposition. So it's complicated, is all I can say. But certainly they did recognize that clearly closeness was associated with brightness. But again, in general, if a planet was generally, or a star, for example, they thought of Sirius as a big star because it was so bright. So that's kind of the proxy that they used. Okay, so let me go through a little bit of the math. I'm running out of time, and I do want to show at least one piece of math. The orbits, I think, will skip. Copernicus, for the first time, is able to now calculate the actual true orbits, called the sidereal orbits, the orbits of the stars, actually the orbits of the planets going around the sun. This was not a notion in Ptolemy's system. The orbits are going around the Earth, but he's actually able to do this. I won't go through this math because I want to go through the sizes of the orbits, which are simpler and so beautiful. But the calculations that he gets for Mercury and Venus are this. These are the orbits that he finds: 88 days for Mercury and 225 days for Venus. Here is the very pretty formula that the period of the orbit of either Mercury or Venus is the synodic period times our period of 365 days. It's S times T over S plus T. Very, very pretty equation that you get to be able to calculate these numbers. S is the synodic period. It's the time it takes to get from one position with the sun to another position with the sun. The simplest example would be the full moon. The full moon is 29 days. That's the synodic period of the moon. It's when the moon is in opposition to the sun, to the next opposition. Well, the same thing with the planets. You can go from opposition to opposition or conjunction to conjunction. Those would be the synodic periods. And from that, Copernicus is able to calculate the true periods of going around the Earth. And we get these numbers for Jupiter and Mercury and Venus, and we get these numbers for Mars, Jupiter, and Saturn. And they're very, very accurate. Okay? They're very accurate numbers because the formula is accurate, and measuring the synodic period is relatively simple. You're going from opposition to opposition. Okay, it's not a hard number to measure. But here, before we go, with the 5 minutes I have left, I want to show you how Copernicus calculates the distance from the planets to the sun, and therefore relative to the Earth. So we'll take Venus and Mercury first. And Copernicus says, so wait until we get to maximum elongation. Wait till Venus is at maximum elongation with the sun. We know what that angle is, right? That angle is 45, 46 degrees, whatever. At that point, at maximum elongation, we know that the line of sight of the Earth to the orbit of the planet is just tangent to that orbit. And therefore, with a fundamental property right out of Euclid, that a line tangent to the radius line is perpendicular. So he has a right triangle. Here is the radius of the orbit of Venus. Here is the radius of the orbit of the Earth. And isn't the sine of this angle the opposite over the hypotenuse? Isn't the sine of this measured angle, the angle of elongation that the sky watchers have known for thousands of years, is the opposite over the adjacent? If we call this 1, if we call this the distance from the sun to the Earth 1, which astronomers do, it's called 1 astronomical unit, we get the formula that the radius of the planet is simply the radius of the Earth times the sine of the angle of elongation. And there's the calculation. So Mercury is 0.39, our orbit, and Mercury is 0.73, coming from the fact that the sine of the angle is the opposite over the hypotenuse. How pretty. And Mars, Jupiter, and Saturn, a little bit more complicated, and therefore maybe even a little prettier. Copernicus says, start at opposition and wait until Mars and the Earth become at maximum, at 90 degrees elongation. Wait until the angle, this separation in the sky between Mars and the sun is 90 degrees. And we have formed another right triangle, okay? Wait, the amount of time it takes so that the angular separation in the sky that we see from the Earth between the planet and the sun is 90 degrees. And we have another right triangle. And if we could just figure out this angle, then isn't the cosine of this angle the adjacent over the hypotenuse? The cosine of this angle would be the adjacent over the hypotenuse. Calling this 1, we again will get a measure of this distance from the sun out to the planet. Okay, this turns out to be 105 days. And so look at what this angle B is. This is the whole orbit of Mars, which we now know. So this is 105. So the angle B is to 360, as 105 is to the period of Mars, 687, which we measured in the previous slides. So therefore we get angle B of 55 degrees. And also the angle of A and B together, well, this is 105 degrees over 360. Angle A plus B is to 360 as 105 is to 365. So we get A plus B is 104. We know A plus B, we can subtract and get B. Angle A. Angle A is 48 degrees. And the cosine of A, again, is the adjacent over the hypotenuse. Is RE over RM. So the radius of the orbit of Mars is 1 times the cosine of 48 degrees, and you calculate that to be 1.52. Jupiter and Saturn are done exactly the same way. Okay, you start with opposition, how long it gets to get to elongation of 90, and you do the same kinds of proportions. And here is this data. Take a look at Copernicus's numbers of the relative distances of the planets compared to the Earth, calling it 1, compared to our modern numbers. Impressive, no? Why so close? Because these measurements are relatively easy to take. These measurements don't take a high sophisticated technology to get them pretty accurately. And that's why his numbers are pretty accurate compared to our modern numbers. We're taking, angles that are relatively easy to take in the sky. And so Copernicus's numbers are quite accurate. The orbital periods, again, as we didn't go through this math, and from the sizes of the orbits and the orbital periods, distance over time will give us the speeds of the planets, the average speeds of the planets going around the sun. And we can see, yes, they are going slower and slower as we get further and further away. Okay, why is that? No, is that a coincidence? It's empirically the case now. Copernicus has shown it to be the case. A question that could be raised. And finally, we'll stop here. Take a look at Ptolemy's numbers. I didn't put in Mercury and Venus. It's not fair because, they're not really going around the sun in that sense. So it's not comparing apples to apples. But here, these are fair. Remember how far away Mars had to be in that big epicycle. Okay, the size of the deferent of Mars, of the orbit of Mars compared to what Copernicus finds. Jupiter, half, and Saturn, 50%. What Copernicus has done to the solar system, if I can use that anachronism, what he's done to the size of the planets is he's shrunken it by 50%. Okay, the size out to Jupiter is 50% smaller than Ptolemy's system. But the fixed stars are vastly beyond the fixed stars of Ptolemy. Although he has exploded the size of the universe in general with the celestial sphere, he has shrunk down the size of the distance of the planets going around the sun. Okay, we'll stop here and we'll finish up Copernicus next time. Questions or comments before we go?
A question. Your classes are way over my head, but I enjoy stretching my brain. That said, could you tell me very briefly why Copernicus thought the sun was the center rather than the earth?
Well, see, that is a great question. So this is not over your head. That is a very central question. Being a humanist, being part of the Pythagorean Platonic tradition, as opposed to the Aristotelian, one of the great things in that tradition was the importance of the sun. So it was very natural for him to think of the sun. And he has a beautiful line somewhere in the work that talks about the sun being the temple of the universe, that it is the source of all light and of all heat, and therefore of all earth, of all life on the earth. And of course, the great sun would be at the center of God's creation. It's an excellent question.
It wasn't science, it was just his belief.
It was his belief going back to the, like I say, the Pythagorean tradition.
I'm very impressed with the mathematics, because who created these formulas? He must have created them, right? How to figure these distances?
Of course. Yes, of course. He
Phenomenal.
Yeah. No, but once you take the decision that the sun is at the center, you begin to build this geometry. And like I say, you don't have a lot of choice. The elongation of Mercury is what it is. And therefore, the distance out to Mercury is the sign of that number. There's not a lot of choices here once you begin to buy in to the model, the framework that he has. Any other thoughts, questions, comments? Okay, guys, we will finish this up next time, and we'll begin. See, we aren't really at a revolutionary point here, are we? This is not, yes, the Earth being in motion is quite revolutionary, but in and of itself, you know, the rest of this is quite, the mathematics he's using is all of Ptolemy's math, not even all of Ptolemy, he refuses to use some of it. The revolution hasn't quite happened yet, and we'll see that as we finish the talk and get into our next presentation. All right, guys, I will end the recording, and we'll see you next time.